plot the point minus 1.32 plus 1.5j in the diagram as well. So minus 1.32, get that down here somewhere, 1.5, so that gives us this point here. That's our design point. So once we've got that far, it is now a matter of applying the angle criteria to this problem. And so we have to work out now, draw straight lines from this point to all the poles and zeros, measure all the angles, and then stick it into the angle criteria. And we should from that be able to calculate where T is. That's the trick. So here we go now. So we'll start drawing lines in. There's our first one. So there's quite a few lines to draw now. This is the only unfortunate thing about this particular design. So we just have to keep on drawing the lines in. I've tried to make this quite big so as we can get some reasonable accuracy in it. And there's one more to finish off over here. If I get them in nicely. So we've now drawn in all of our lines to all of our poles and zeros, and we can now start to measure angles. Now remember the poles, we're going to use betas, and for zeros we're going to use alphas. So we can now start to measure angles. So draw that line here, so that could be beta 1. Remember, to measure angles you're going to need a protractor. This is one I specially made, so you could go up to here and you could then measure beta 1. So beta 1 might be about 150 degrees in my reckoning, but you'll have to measure them all. Then we could measure, this one here is going to be on the pole, it's going to be beta 2. This one here could be beta 3. Another pole here, that could be beta 4. Another pole here, that'll be beta 5, but we don't know beta 5 yet, so that's the sort of one we have to watch out for. And beta 6 here. So we've measured all of the pole angles, but we notice now that beta 5 is associated with the washout filter, and that's the unknown. So beta 5 now is the thing that we're after. We can now, I've missed a 0, have I? No, I've not missed a 0 now. Right, so then we can then measure the angles of the zeros. So draw that line in there, so that we can call that one alpha 1. This one here would be alpha 2. Got another 0 here, alpha 3, and we've got another 0 here, which is alpha 4. Remember, there's a pole and a 0 at the origin there. So we can measure all these angles. Got a bit of a protractor on there. This one's probably about 40 degrees. So measure all angles. So then we're going to stick this now into the angle criteria. Which is very straightforward. Remember, the angle criteria says that the sum of the 0 angles minus the sum of the pole angles adds up to exactly minus 180 degrees. So we can now get our 0 angles, and in our 0 angles we've got alpha 1, alpha 2, alpha 3 and alpha 4. So we have alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 minus, and then we've got beta 1 plus beta 2 plus beta 3 plus beta 4 plus, I'm going to put in red, plus beta 5 plus beta 6 is equal to minus 180 degrees. Now, if we look at this expression here, we'll have all these parameters other than beta 5. So we can solve this for beta 5. And then once we've got beta 5, we draw a line along here. That's parallel to these axes. And then what we do is we measure now down this way, this angle here is beta 5. So we measure down beta 5, and it comes down here, and where it crosses, then this distance here is in fact t. That is t. So from there to there, measuring in that direction would be t. If we do this correctly, t comes out, t should come out as 0.35. So we're halfway there now. We know that t is 0.35. And we've got that using the angle criteria. So we can now move on to the last stage, which is to get Kr. So to get Kr, we do away with the angle criteria. We know now where this is, and we can go ahead now with using the magnitude criteria. And the magnitude criteria says that Kr multiplied by the forward loop gain, so we've got a 2 in there, a 1 in there, a 1 in there, and a 1 in there, so it's going to be 2. So Kr times 2 times, now we'll have to go back to this diagram now and start measuring angles, or measuring distances, not angles this time. So this time we're going to, if it's a pole, we're going to call it an mi, and if it's a 0, we're going to call it an mi hat. So we can now go back to get our ruler, if we have some scales on, and we could now measure the different distances and then stick them into the magnitude criteria. So we could measure this one here as m1, we could measure that one there as m2, so actually m2, we could measure that distance there as m3, we could measure that distance there as m4, this distance here could be m5, and finally that one there would be m6. So they're all the distances associated with the poles. Go back now, get the zeros. There's a 0 there, so we could call that one m1 hat. Got another 0 here, so that one could be m2 hat. Got another 0 here, so that could be m3 hat. We've got another 0 here as well, so that would have to be called m4 hat. In fact, m2 and m4 hat are the same, but we'll keep them in for completeness. I hope this doesn't get too complicated. It looks complicated. So then, the magnitude criteria says Kr times the product of the 0 distances. So that's going to be m1 hat, m2 hat, m3 hat, m4 hat, divided by the product of the pole distances. So there's 6 of those, so it's going to be m1, m2, m3, m4, m5, m6, and that's going to equal to 1 always. So remember the magnitude criteria says Kr times the forward loop gain times the product of the 0 distances over the product of the pole distances is always equal to 1. And in this equation now, we know everything but for Kr. So we can solve that for Kr, and in this particular case, Kr comes out as 2, which is quite nice. So that would be a 2 in there. So this now is the design of our yaw damper. It's got a forward loop gain of 2 and a pole here in the washout filter at 0.35. And we've achieved that Just to recap, we start off, work out the poles and zeros, work out the desired pole. The desired pole gives us this point here, plot all the poles and zeros, then apply the angle criteria to get out to this little parameter here. And then once we've done that, we can then locate that point. We can then go back to the diagram, measure all the distances, put into the magnitude criteria, and then that will give us the gain KR. And that concludes the design of the damper. Thank you.